relation is a very important part of modern algebra, and to know relation, it is necessary to clear the concept of Cartesian product. So at first we are discussing about Cartesian product of two sets. Suppose A and B are two non-empty sets. A and B are two non-empty sets. Then what is the definition of their Cartesian product? Cartesian product is denoted by A cross B, and it is the collection of all ordered pairs x, y such that the first component, that is x component, belongs to first set A, and the second component y belongs to second set B. So if A and B are two non-empty sets, then their Cartesian product is the collection of all ordered pairs x, y such that the x component, that is first component, belongs to first set A, and second component y belongs to the second set B. So let us give some example. Consider the sets A and B as A is 1, 2, that is a set consisting of two elements 1, 2, and B is another set A, B, C. B has three elements. Then A cross B, Cartesian product of the sets A, B is the collection of all ordered pairs x, y such that x belongs to first set 1, 2, and y belongs to second set A, B, C. So we can see there are two options available for x, 1 and 2, and there are three options available for y. They are A, B, C. So what are the all possible ordered pairs created? 1, A. If we choose x equals to 1, then y may be A, may be B or C. So starting with 1, we can get three ordered pairs: 1, A, 1, B, 1, C. Similarly, if we start with 2, there are three options available: 2A, 2B, and 2C. So this is the complete Cartesian product of the sets A and B. Suppose we are doing B cross A. B cross A means Cartesian product between the sets B and A. Then the first component will be selected from the set B, and second component will be selected from the set A. So all possible ordered pairs formed are A, 1, A, 2. Similarly, if we start with B, we will get two options B1 and B2. Finally, starting with C, we shall get two ordered pairs. So clearly from the above Cartesian product, we can conclude that A cross B and B cross A are different in general, but there is a similarity. A cross B has 6 number of elements, B cross A has again 6 number of elements. So number of elements present in the set A cross B and number of elements present in the set B cross A are same. So this is the basic idea of Cartesian product. Now we shall discuss about relation. What is a relation? In general, we are doing binary relation. Binary relation means relation between two sets. So what is a binary relation? A binary relation between the sets A and B is any subset of A cross B. Since we are using two non-empty sets, that is why this type of relation is called binary relation. So if A and B are two non-empty sets, then a binary relation between A and B is any subset of A cross B. So we assume A as the set 1, 2, B as the set A, B, C. So what was A cross B according to our previous example? So according to previous example, A cross B is equal to 1, A, 1, B, 1, C, 2, A, 2, B, 2, C. Let us consider the set rho is equal to 1, A, 1, B and 2, B. So clearly we can see the first element of row 1, A belongs to A cross B. The second element of row, which is 1, B, again belongs to A cross B. The third element of row, which is 2, B, belongs to A cross B. So clearly, each element of row belongs to A cross B. Each element of row belongs to A cross B. Hence, according to definition of binary relation, we can say rho is a relation between A and B as rho becomes a proper subset of A cross B. Since each element of rho belongs to A cross B, so rho is a subset of A cross B, and we know any subset of A cross B is called relation between A and B. Therefore, our assumed set rho has become a relation between the sets A and B. Consider another set. Let us consider sigma is equal to 1 comma b, 2 comma b, 3 comma b. So we can see the element 1 comma b of sigma belongs to A cross B. The second element of sigma 2 comma b belongs to A cross B, but the third element 3 comma b does not belong to A cross B. Clearly, the third element of sigma, which is 3 comma b, does not belong to A cross B. Therefore, sigma is not a subset of A cross B. Therefore, we can say sigma is not a relation between A and B. So, the basic definition of a relation between any two non-empty sets A and B is any subset of A cross B. Next, we have to find the number of relation between any two sets. Let the set A has P elements and the set B has Q elements. Therefore, we can say number of elements belonging to the set A cross B is the product of number of elements in A and number of elements in B. That means P into Q. Therefore, number of relations between A and B is equal to number of subsets of A cross B, since A cross B has a total of PQ elements. So total number of subsets of A cross B is 2 to the power PQ, which can be written as 2 to the power NA into NB. This is the basic formula to find the number of relation of two non-empty sets. Previously, we have considered A cross B as 1, A, 1, B, 1, C, 2, A, 2, B, 2, C, where A was the set 1, 2 and B was the set A, B, C, and the relation considered was a row that was 1, A, 1, B. Let row is a relation which is 1, A, 1, B and 2, B. So what is domain of the relation? Domain means collection of all elements from A for which x, y belongs to row. That means if an ordered pair belongs to the relation, then its x component, that means first component, will belong to the domain of the relation. So domain is the collection of all x components. So according to our above relation 1, A, 1, B and 2, B, we can say the x components are 1, 1, 2. So collection of all different x components is 1, 2. So for the relation row, domain is 1, 2. Similarly, what is range of a relation? Collection of all y components. Y belongs to B for which ordered pair xy belongs to row. So we can see that the y components for the ordered pairs belonging to row are A, B, B. Therefore, range of the relation row is A, B. And finally, we have to know about inverse relation. So what is inverse relation? Inverse relation of row is denoted by row inverse, is the collection of all ordered pairs reversing the order. That means 1, A belongs to row. So its reversed ordered pair A, 1 will belong to inverse. 1, B belongs to row. So its reversed B, 1 will belong to row inverse. 2, B belongs to row. So its reversed ordered pair B, 2 belongs to row inverse. So it is clear that as 1 comma A, 1 comma B, 2 comma B, these three ordered pairs belong to row. So they are reversed ordered pairs. A comma 1, B comma 1 and B comma 2 must belong to row inverse, the inverse relation. So what will be the domain of the inverse relation? Collection of all x components for the ordered pairs A comma B. What is the range of the inverse relation? Collection of all y components, which is 1 comma 2. Now comparing with the above equations and above relations, we can say domain of inverse relation is equal to range of original relation. Similarly, range of inverse relation is equal to domain of original relation. So this is the basics of Cartesian product and relation. Cartesian product of two sets A and B is the collection of all ordered pairs where first component belongs to first set and second component belongs to second set. Total number of elements of the Cartesian product A cross B can be obtained by multiplying number of elements in A and number of elements in B. What is a binary relation? A binary relation between the two non-empty sets A and B is any subset of A cross B. Domain of relation means collection of all x components. Range of relation means collection of all y components. And the most important part is we have to choose x and y components for those ordered pairs which belong to the relation. And the final conclusion is domain of inverse relation is equal to range of original relation. Similarly, range of inverse relation is equal to domain of original relation.